goal of the project is to develop an efficient stochastic simulator based approach for seismic UQ analysis of bridge response. And we have three technical aims. The first one is to develop the stochastic surrogates model for the stochastic simulator. And the second one is to perform forward seismic UQ analysis for bridge response. And the last one is to analyze the sensitivity indices of bridge response with respect to different types of uncertainty. In seismic UQ problem, we need to consider different types of uncertainties, which is arising from the ground motion variability or structural parameter uncertainties. And seismic UQ analysis aims to quantify the statistical property of the output, for example, the joint PDF of the EDP vector or correlation coefficient matrix or their fragility function. So in this research, we aim to develop the stochastic simulator and to perform the forward UQ analysis and to perform the sensitivity analysis of seismic response with respect to these different sources of uncertainty. First, development of the stochastic surrogate model. In this chapter, in this section, our target is to develop the stochastic surrogates model to reduce the high computational cost caused by the iterative nonlinear response time history analysis. However, the surrogates modeling can be challenging due to the complex and high-dimensional input uncertainty, especially for the ground motion uncertainty. So in such a case, the dimensionality reductions can be useful. So we propose the dimensionality reduction-based stochastic surrogates modeling method. The main idea is to perform the dimensionality reduction in the input-output space. So we project the high-dimensional input, for example, the ground motion, augmented with their physical output, for example, the seismic EDP, into the reduced feature space together, and train the manifold model, and then extract the surrogates model from the result of the dimensionality reduction. So this is a kind of main idea and basic concepts of the proposed surrogate model method. And here's the procedure of the proposed surrogate model method, and we have only 3 steps. In the first training stages, we do the dimensionality reduction in the input-output space, so we map the input-output into the reduced feature space. And in the second stages, we construct the conditional distribution model to predict y given v. So in these training stages, we can construct the following interdependency structures involving the true surrogates model. And this true surrogate model involves the constructed the conditional distribution model and a dimensionality reduction. On the other hand, in the prediction stages, our technical target is to extract the surrogates model from the result of the dimensionality reduction. So here, we have made an approximation by introducing another random variable denoted as y prime here, and we found that if we iterate the transient surrogates modeling using y prime, we can finally obtain the stationary surrogates model that involves the transition corner. And these transition corners involve the constructed the dimensionality reduction mappings and a conditional distribution model. And this means that if we simulate the random samples following the transition corners, we will obtain the stochastic samples of our stochastic surrogates model. So I summarize some main characteristics of the proposed surrogate model. Because we extract the surrogates model from the result of the dimensionality reduction, our model is a model for the surrogate. Our model is for surrogates model for the high-dimensional system. And our model is a stochastic simulator, so output prediction or probabilistic distribution, not a deterministic prediction. And our output is a multi-output predictor, so we can quantify the interdependency effect or correlation coefficient between the multiple output. Next, we perform the seismic UQ analysis using the stochastic simulator model. So here, we first consider the ground motion variability, which can be represented using the synthetic ground motion generated by the ground motion model or recorded ground motions obtained from the database. And in this ground motion, we consider each ground motion as a realization of the stochastic process defined at discretized time point. And we consider the structural parameter uncertainties in bridge model, which can include the structural damping or material property. And based on the paired input of the ground motion and structural parameter, we can perform the linear response time history analysis, and by iterating this process, we can finally quantify the uncertainty in the seismic response of bridge. So here, we replace this nonlinear response time history analysis by using our developed stochastic simulator model. And this is a structural model that we applied, and this is the urban ravine structures, a PSC girder back bridge featuring 6 spans and 2 piers per band. So here's the elevation, and here's the cross-section of the girders, box girder shapes. And we consider the 12 uncertain structural parameters in the bridge model, which include the structural damping and material property and geometric parameter. And for bridge EDP, we consider the drift ratio of the each pier and bending moments of the each girder's element. So these critical bridge EDPs are the outputs of our stochastic simulator model. For the ground motion, we first collected the recorded ground motion, and this is the 2000s recorded ground motions obtained from the pier NGA West2 database. So given the seismic hazard parameter, we define the target response spectrum using the ground motion model, GMP equations, and spectral correlation structures. And then we selected 2000 spectrum compatible ground motion data set using the ground motion selection algorithms. So this figure represents the response spectra of the selected motion, and this figure represents the histogram of the PGA for the selected motion. So in this problem, the input is the pair of the structural parameter and a ground motion, and the output is the critical bridges EDP, such as the pier drift ratio or girder's bending moment. And here's the surrogates modeling result of seismic response, and this is the result for the pier drift ratio. So first, we train our surrogates model using 600 training data, and we test the performance of the stochastic simulator models using 1,400 test data set. And this is the scatter plot comparing the true seismic response with the stochastic simulator-based prediction result. So in each figure, the blue dots represent the true seismic response, and a black solid line and a gray shaded area represent the predictive mean and predictive standard deviation intervals by the stochastic simulator model. And this is the result for the first, third, and fifth pier of the bridge models. And the below table represent the mean peak values of the pier drift ratios, and we can find that the stochastic simulator model can predict the seismic response that is compatible with the Monte Carlo simulation result using the iterative open seas model with the error below 3%. And here's the UQ result for seismic response, and this is the marginal response PDF, and this is the correlation coefficient matrix of Gödel's bending moment in two axes, y-axis and z-axis. And in this figure, the stochastic simulator-based prediction results are compared with the brute force Monte Carlo simulation result. And we can find that the proposed simulator can capture the global behavior of the seismic response, such as the marginal PDF and correlation coefficient matrix. And then now, we apply the stochastic simulator model to synthetic ground motion case. So similar with the previous case, we generated 2,000 spectrum-compatible synthetic ground motions using the ground motion generation algorithms. And this is the seismic UQ result under the synthetic ground motion scenario. So this is the marginal response PDF, and this is the mean peak value of the Gödel's bending moments across the longitudinal position of the deck. And we can find that the error is just below 5% in this case, and the stochastic simulator model can be applied to both recorded and synthetic ground motion scenario. Next, we perform the sensitivity analysis of the seismic response using the stochastic simulator. So the variance-based sensitivity analysis or the global sensitivity analysis are widely used to quantify the relatively contribution of input variable to the output variance. So we computed the sensitivity indices of each EDP with respect to each groups of input uncertainty. So we computed the sensitivity of the bridge EDP with respect to ground motion uncertainty and a structural parameter uncertainty. And these sensitivity indices can be represented like this equation. And evaluation of these sensitivity indices is really challenging because it involves the high-dimensional input variables such as the ground motion time history and a high computational cost. So we apply the proposed stochastic simulator model in a sensitivity analysis. And this is the sensitivity analysis result of the seismic response. So this first column represents the result for the shear force of the Gödel, and the second column represents the axial and bending moments of the Gödel. And in each figure, the blue line represents the ground motion sensitivity, and a red line represents the structural parameter sensitivity, and a yellow line represents their corresponding interaction effect. So in this figure, we can find that the ground motion sensitivity is much bigger than structural parameter sensitivity. So the relative contribution of the ground motion is usually larger than 60%, while the structural parameter sensitivity are usually below 20%. And in this figure, the prediction result are represented by the dashed line, and the solid line represent the reference solution, and we can find that the stochastic simulator prediction error are usually below the 10% in such case. And this is the recorded motion case. And this is the sensitivity analysis result under the synthetic ground motion scenario. And we can find that the same trend are observed in this synthetic ground motion scenario, and the ground motion sensitivities are much bigger than structural parameter sensitivity. So here's the summary. So for the seismic UQ analysis, we developed the stochastic simulator model and performed the seismic UQ analysis and performed the global sensitivity analysis. And here's the related reference, and the peer report will be submitted in a few weeks. And I also want to wrap up my presentation by introducing one of the promising future direction for seismic UQ analysis. The current proposed simulator model can predict the structural response at a vector scale, such as EDP vector. However, the prediction of the complete continuous structural response functions remain limited. So neural operator can be a good option for predicting the continuous response function. So unlike the traditional neural network model, neural operators aim to run the underlying mathematical operator that govern the system rather than point-wise approximation. So this is a kind of a function-based learning. So given the input function, for example, the ground motion, and output function, for example, the structural response, the neural operator construct this kind of projection and lifting and a convolutional layer of the kernel operator. So through the iterative kernel integration, the integrating of this neural operator into the stochastic simulator models can be a promising research topic for seismic UQ analysis to predict the time series displacement or velocity profile or full field stress distribution under the seismic excitation. So identifying the joint feature or joint PDF of the input function and output function within the stochastic simulator frameworks can be a good directions for capturing the spatial and temporal pattern in structural response. So this is all of my presentation, and thank you for listening.